morning again. And we're going to start our first topic of divergence. And so the question is, what is divergence? And divergence has a technical meaning in aeroelasticity. It's a term that's sometimes used outside of the field of aeroelasticity per se. Generically, it's a bit like buckling in the sense that it's a static instability, meaning that we can do a static analysis rather than a dynamic analysis, which is why we're discussing it first, but statics is easier than dynamics, right? Now, you can do a dynamic analysis, and that will produce the divergence condition, and sometimes you can gain some additional understanding of divergence by doing that. We're not going to do that yet, because we want to keep things as simple as possible. So, and beyond that, we're going to use a classic configuration that is loved by generations of aeroelasticians. And it's a very simple one, but it's one that could be realized physically in our wind tunnel. So I want to talk a little bit about that. So here we are on August 27th in the year 2024.
Yeah, that's weird.
Am I upside down or backside?
Challenge.
I didn't do that, did I?
I don't think so.
Unless you wrote it like that.
Looks like I'm looking in a mirror.
It is. Hmm.
I still in my head.
Uh-oh. Let's see. This keeps wanting to disconnect for some reason.
Mm-hmm. Well, while we're playing with that, so we'll talk about divergence. We'll find out what that's all about. We'll have a mathematical model, which we like. As I mentioned, it can also be realized physically, we hope. You need to sit here?
It's okay. I think I got it. But I don't know how to unmirror it yet. Turn video on. Okay. Now we got to figure out how to mirror. There we go.
Oh, there you go.
Okay.
Oh, I like that better. I bet everyone else does too. Thank you. Thank you. Okay. So here's the math model. And also, as I said, something you might actually put in the wind tunnel. So let's think of this being, for example, the ceiling, this being the floor. And here we have a very thin and very stiff, technically a rigid, i.e. it doesn't elastically form. But since we're discussing aeroelasticity, we need some elasticity. So the simplest kind of elasticity we can imagine would be to place a spring at this point and say attach it to the ceiling or the floor, it doesn't matter. And this is meant to be a torsional spring. So when I twist the wing, the spring wants to twist it back, right? So I have a moment due to that spring. I also have a moment due to the aerodynamic flow at some velocity of infinity. And yeah, hope that doesn't bother you. It doesn't bother me. And it's really a balance between those two moments that this determines how this will twist, right? It turns out if the airspeed is high enough, our simple mathematical model will predict that the twist goes to infinity. Well, of course, it doesn't in the wind tunnel. And the only reason it goes to infinity in our math model is because we're going to use a linear model, at least initially. But if I put a nonlinear, some sort of nonlinearity in the math model, then there would be a finite twisting. But below that magic flow speed, if I'm initially at exactly zero angle of attack, zero orientation to the oncoming flow, there will be no twisting at all. And then suddenly, at some magic angle, it twists. This is called a bifurcation. I don't know if that's a word that you use or not, but it's a term that mathematicians like. Some qualitative change occurs at some magic value of a parameter. In this case, the parameter is the flow speed. Okay, so we need to write down an equation of equilibrium, torsional equilibrium. The only thing our simple model can do is twist, right? That's the only thing it can do. Later on, we'll have models that can have more complicated combinations of motion, but here it's all it can do is twist. So the moment due to the spring,
Off the page, Dr. Dunn.
oh, sorry about that. The moment due to the spring plus the moment due to the aerodynamic flow is summed to zero. So what's the moment due to the aerodynamic spring? Well, the moment due to the spring, we will assume is equal to some constant, I'm going to call it k sub alpha, that's the property of the spring, times alpha sub e, where alpha sub e is the elastic twist of the spring.
Could you move the page up, Professor?
Sorry about that. Thank you. Keep telling me that, because I tend to not look up as often as I should. Okay. And so this is a linear model, right? I could add another term. I could add something that goes like alpha E cubed. If I, and most springs, if you twist them enough, do have a nonlinearity in them, but for small angles, they don't. And this is just some property of that spring, which I can measure, by putting a specified moment on the spring and seeing how much it twists, right? Or I look it up in the catalog if I believe the manufacturer is reliable. Okay. Now the moment due to the aerodynamics is traditionally written in the following way. It's equal to a lift force. That's the total force on this airfoil, okay, due to the aerodynamic flow, times a certain distance, e, which we'll talk about in a moment, plus another moment with the subscript MAC. Now, why do we do that? Well, aerodynamicists like to do this. I mean, that's what it is. But why do they like to do it? Well, you can find a point on this airfoil. So this I'll give it a name. I'll call this point elastic axis. That is a more general concept. In this context, it's just the point where the spring is attached, right? But there's another point up here, and I'll call that the aerodynamic center. By the way, I see you all diligently copying this down, and that's great. But Alex promises me he will take these notes and put them on Canvas. So you're welcome to scratch as much as you like, or you can just put down little things that either prompt a question you're about to ask or make some profound comment that you observe based on what I've said. So you don't really need to copy my notes unless you really want to. Okay, now that aerodynamic center, the aerodynamicists define that to be the point along the airfoil where the moment about that point does not depend on the angle of attack. It doesn't depend on the angle at which the airfoil makes with the oncoming flow. There always is such a point, by the way. Okay. And then we think of this point as having two components to the moment. One is a moment that doesn't depend on angle of attack, it's this piece, plus the lift, which does depend on the angle of attack, as we'll see in just a moment, times the moment arm, that distance, E, which is the distance from the aerodynamic center to the elastic axis. Yes, sir.
So like for a NACA 0012, is the aerodynamic center around 25% of the chord? Is that?
It is.
Okay.
It's actually in subsonic flow, it's about, it typically is about 25% of the chord for almost any airfoil of reasonable construction. In supersonic flow, it turns out to be at the 50% chord. So it moves with Mach number. So in low speeds, it's the quarter chord, and supersonic flow, it's the half chord. As I move from low speed to high speed, and I go through the transonic range, it moves from the 25% chord to the 50% chord. Yeah.
But it's not dependent on angle of attack, only the velocity.
It depends on the Mach number more
Mach
specifically.
number.
It depends on velocity per se. It depends on the Mach number.
Thank you.
Yeah. In fact, why don't I write that down? E is equal to C over 4. That's for subsonic flow. Mach number is less than 1. It's equal to C over 2. Oh, sorry about that. For Mach numbers greater than 1. And for a real airfoil, somewhere around Mach 0.7, it starts moving backward. For strictly speaking, for a flat plate, infinitely thin, it would jump as you go through Mach 1 from the quarter chord to the half chord. But for a real airfoil, which has finite thickness and maybe curvature or camber, it would start transitioning from 0.25 or quarter chord to the full half chord or the half chord, say around the Mach number 0.7, and then it might not get quite to the half chord until you get to a Mach number of 1.1, right? In the transonic range, a lot of things are important in the transonic range that are not terribly important at either very low speeds or very high speeds, which is one reason why transonics is more difficult. Yes.
How can it, I know about the aerodynamic center, but how can it be true that it's not dependent, the moment is not dependent on angle of attack? Because as you pitch your airfoil, the center of pressure is moving along and that changes.
It's true if the angle of attack is small enough. It doesn't depend on the angle of attack if the angle of attack is small enough.
Okay.
Okay. And how small is small enough? It turns out, if I'm at Mach number 0.1, which is our wind tunnel, up to maybe even 10 degrees. If I'm at Mach number 0.9, it might be 1 or 2 degrees. See, that's another difficulty with transonic flow. The range of linearity for which these aerodynamic models apply is much smaller in terms of the allowed motion before you get into the non-aerodynamic.
What does E stand for again?
Say again?
What does E stand for again?
Where's the,
E, what does it stand for?
which one now?
Is it?
E,
Yeah.
oh, E is the distance from
Oh,
the
that's the
aerodynamic
distance.
center
Okay.
to the elastic axis.
Got it.
And by definition, E is positive when the aerodynamic center is ahead of the elastic axis. So what I'm saying is low speed flow, this aerodynamic center is roughly the quarter chord. Of course, this spring point can be wherever we choose to attach the spring, right? And we'll see that E is really important in divergence. Okay. I mean, a lot of things are important, but E is certainly important. Oh, I said the wrong thing. I said E, and that's not right. Sorry about that. The aerodynamic center is at the quarter chord in subsonic flow and half chord in supersonic flow, as measured from the leading edge, right? I'm sorry, but E is then wherever that aerodynamic center is, the distance from there back to where the spring is attached. Sorry about that. Okay. Are we okay so far? All right. Now, let's talk a little bit more about how we represent lift. The lift is going to be written as Q. I'll tell you what Q is in a moment. C, I'll tell you what C is in a moment. CL sub alpha, I'll tell you what that is in a moment, times alpha, where alpha is the angle of attack. And we think of it as being composed of two contributions. One is the initial angle of attack the airfoil might have when the spring is not deformed, when the spring is not twisted, plus an alpha sub E, which is the twist of the spring. So this is the twist of the spring. Oh, sorry about that. Twist of the spring. And this is the angle of attack with no twist, i.e. alpha E equals 0. So we have two contributions. The aerodynamics depend on alpha. So the aerodynamics depends on whatever initial angle we set, plus some additional angle because of the twist of the spring. And it's this twist of the spring that changes the aerodynamics that leads to the possibility of divergence. Q, you have to learn the language. Q, is called the dynamic pressure. It's a little bit of a misnomer, but the name is lost to history, and we probably want to call it the same thing, because that's what everybody else wants it. And it's equal to 1/2 rho infinity times U infinity squared, where rho is the density of the flow and U infinity is the flow velocity. In our low speed wind tunnel, that's just the density of 1 atmosphere, whatever that is. By the way, if you don't know this, I'll just tell it to you, but you can also write it a different way. You can write it with 1/2 gamma P infinity Mach number squared, where this is in our low speed wind tunnel atmospheric pressure. In our low speed tunnel, the Mach number is about 0.1 because speed of sound is 343 meters per second, and with my test at about 34.3 meters per second, right? So we're at Mach 0.1. We're not at a very high Mach in our low speed wind tunnel.
Gamma being 1.4.
I'm sorry?
Gamma being 1.
Gamma is the ratio of specific heats, and in air it's 1.4. Yeah. So you may have taken a course in compressible flow and you know this. If you haven't taken a compressible flow course, you're taking my word for it as a scholar. Whatever. Okay. C is the chord of the airfoil. We need to know that. Chord of the airfoil. Sorry about that. CL alpha is a non-dimensional number. It's the number that makes this formula true. Where does it come from? Chapter 4, or A Course in Aerodynamics. Okay, but for our purposes, I'm just going to tell you what it is for our case. CL alpha is equal to 2 pi divided by 1 minus the Mach number squared, square rooted. Square rooted. Okay, that's when the Mach number is less than 1. That's equal to 4 magic number is 4, divided by the Mach number squared minus 1 square rooted when the Mach number is greater than 1. What happens when the Mach number is equal to 1? Well, CL alpha seems to be fairly large. What that's really telling us is these results, which come out of a linear model for the aerodynamics, comes out basically solving the wave equation for the pressure on the airfoil, breaks down at Mach 1 in 2D flow. It doesn't break down in 3D flow. So I'm thinking of my model as spanning my wind tunnel from wall to wall, so the flow is uniform in the span-wise direction, and these are the results of that case. If I had a finite span wing, these numbers are modified, and thank goodness they don't blow up at Mach 1. But if I have a high aspect ratio wing, the theory isn't that great anyway. It doesn't blow up, but it's not that wonderful. So again, I'm anticipating that someday we're going to talk about transline flow in this course, namely chapter 4. And I'm just warning you that things are going to get a little complicated. But for the moment, particularly if we were going to do an experiment in our low-speed wind tunnel, we could use this formula. The Mach number, if the Mach number were 0.1, this Mach number factor is hardly anything at all. It's just 2 pi, right? That's the magic number. And maybe one other thing while we're here, I'll just show this. You might be curious as to what the pressure actually looks like on the airfoil. After all, it's the aerodynamic pressure on the airfoil that's giving rise to the lift and the moment and all that good stuff. And it turns out to be the following. Typically, you plot P, the local pressure, minus P infinity. That's 1 atmosphere. That's 14.7 psi or whatever. Divided by Q, because Q has the dimensions of pressure, right? It's density times velocity squared, or here you see gamma's a number, 1.4. This is a Mach number, which is non-dimensional. So Q has the same dimensions as pressure, right? So this is a non-dimensional number. And the aerodynamic theory says that's universal in the sense that if I plot this versus the chord, for example, I'll get the same, for the fixed Mach number, I'll always get the same answer. Okay. And for a small enough angle of attack, everything will be proportional to the angle of attack. So this pressure distribution looks like the following. If I go from here, X is the coordinate along the airfoil. I go from 0 up to C. The pressure distribution looks like this. Oops, I meant to go to, it goes to 0 at the trailing edge. Okay. It actually goes to infinity at the leading edge, but it goes to infinity weakly. Weakly means that what happens is the P minus P infinity over Q is proportional to the square root of C minus X, all divided by X. Okay, note when X equals C, of course, this goes to 0. When X goes to 0, it blows up, but it blows up like 1 over the square root. And so when I integrate the pressure to get lift, right? The lift, by definition, is the integral of pressure dx, or usually y1 is the, well, no, dx. And the moment about any axis is p times x dx. And then specifically, if I wanted the moment, aerodynamic moment about the aerodynamic center, I would replace x by x minus c over 4 if I'm in the subside flow, or x minus c over 2 if I'm in the superside flow. So, but the point is, when I integrate this thing, when I integrate a square root singularity, I get a finite answer. So the aerodynamic theory gives you a finite answer for the lift in the moment, even though the pressure is weakly going to infinity at the leading edge. It doesn't really go to the leading edge. It turns out if you add viscosity to the aerodynamic model, it's finite, right? If I run a computational fluid dynamics code, I get a finite answer. But anyway, that gives you a little background, probably tells you more than you really need to know to discuss divergence. But my point is that these numbers didn't just pop out of the hat. They actually come from a classical aerodynamic theory, which we're going to discuss later on, but not understood. Okay? Yes.
So all these equations apply for inviscid flow?
Say again.
All these equations apply for inviscid flow, like we're omitting viscosity? Okay.
Okay. So now let's write down our equation of equilibrium. Let's see, should I? Yeah. Yeah. So let's call that equation one. I don't think I need to number those other equations. So here we are. We have the lift times E, right? Plus the moment about the aerodynamic center minus K alpha times alpha E equals 0. But then we had, I'll write this again so it's all on the same page. We have the lift is QC CL alpha times alpha, but alpha is alpha naught plus alpha E, right? And then the moment about the aerodynamic center, the key here is it doesn't depend. It doesn't depend on the angle of attack. We set it up that way. We looked at the pressure distribution, we computed the moment and so forth, and we found the place along the airfoil where the moment about that particular point doesn't depend on the attack. And we define that to be the aerodynamic center. It's a convention. We don't have to do that, but that's what most people do. So that's what we're going to do. So I could write this as also in a non-dimensional form. I could write this Q. Now this is moment, this is force. So it needs to be Q times C squared times some non-dimensional number. I'll call it CMAC. Okay. All right. Now, what is CMAC, you might ask? Well, the good news is if I really have a very thin, flat, straight piece, airfoil, no thickness, no curvature, it's 0. Okay. It's exactly 0 for 0 thickness. And the aerodynamicists call it camber. We're talking about curvature, right? Camber. So we can carry it along. It turns out we can carry this term along. It turns out it doesn't impact divergence. And if we do that, then if for some reason later on we want to look at an airfoil that's initially has a built-in curvature, then we would put in an appropriate number for this. We ask our aerodynamics friend, what is that number? And they tell us. Okay. Okay, so I'll call this equation 2, I'll call this equation 3. We're going to put 3 and 2 in 1 and see what we get. And here's what we get. We get Q, C, CL alpha times alpha naught plus alpha E times E, that's this term, plus QC squared CMAC, that's this term using this expression, minus K alpha E equals 0. We'll call that equation 4. Oops, sorry about that. Now we're all set up. Now we're just going to do some algebra and see what we get. What we want to do is we want to know how much this airfoil twists, right? We want to know what alpha E is. So let's solve for alpha E. We can do that. I'm going to do the following. I'm going to leave this term on this side and move this term and the one that involves alpha E on that side. That's okay. So I'm going to have Q CL alpha, alpha naught times E, plus Q C squared C MAC. That takes care of that term and this term. And then on the other side, I have K alpha, put it on the other side, that changes the minus to a plus, and that changes this plus to a minus.
Can you move it up a little bit, please?
Not too low thank you. Minus QC CL alpha times E, all multiplied by alpha E, right? And now using higher mathematics, alpha E is equal to this stuff. Divided by this. All right. So this is, I'll just call this comment, I'll call this equation 5. So now we're where we want to be. We look at this and see what happens. Let's start off at Q is 0. If Q is 0, then alpha E is 0, right? We're not blowing on it, and therefore there's no aerodynamic force and moment, and nothing's happening. And then as we increase Q, the numerator, of course, is increasing, and alpha E is getting bigger. But what really causes alpha E to get really big is when the denominator vanishes, which will happen, right? When this aerodynamic factor overwhelms the stiffness of the spring, we're getting a very large deflection. And it's when the denominator is 0 that we call that divergence. So divergence occurs. Sorry about that. Occurs when K alpha minus QC CL alpha E is 0. And now we can solve this equation for Q. But it's not any old Q, it's the Q at which the divergence occurs. So by definition, Q sub D, that means it's the divergence Q, is K alpha divided by C times E times CL alpha. Okay. Note what happens if E is negative. That is, the aerodynamic center is behind the elastic axis. Then the corresponding Q is negative, but that's not physically possible. Or if you prefer, think what happens when E is 0. When E is 0, when the aerodynamic center and the elastic axis coincide, then Q goes to infinity. The divergence Q goes to infinity. So the standard way of preventing divergence is to make sure that the aerodynamic center is behind the elastic axis. Okay. Well, most airplanes cannot be built that way for other reasons. But if you look at rotor blades, if you look at the blades on a helicopter, mostly they put the elastic axis and the aerodynamic center pretty close to each other. And that's to prevent divergence of the rotor. Rotor blades are very flexible. You know? They're very high aspect ratio wings, which happen to rotate. And so rotor blades are prone to aeroelastic instabilities as well. We're probably not going to talk too much in this course about rotorcraft, but there's a chapter in the book on rotorcraft by an expert, not me, but one of my colleagues who is an expert. So if you want to know about rotorcraft, after you've taken the course, you can read that chapter, no extra charge, and find out all the additional challenges of doing aeroelasticity in rotorcraft. Okay, so there we are. Now, let me pause for a moment. Are we all satisfied with this so far?
There's a small mistake in your divergence. There's a small mistake in your equation.
Oh,
on the
which
right.
one?
The alpha should be an E, I think. Under divergence occurs. K alpha minus QC CL alpha times should be E as opposed to alpha.
Which one are we looking at,
Just,
five? Oh, so, well, yeah, that. I got excited, didn't I? Yes, sorry. That should be an E. Thank you. Thank you. I don't know why I said that was alpha. Yes, thank you. Indeed. Of course, I'm supposed to at this point say, I did that deliberately, just to see if you're paying attention. Right? That's not true. I just made a glitch. Yes.
What do you mean when you say aerodynamic center?
Say again.
Well, like, what is aerodynamic center? What is the significance of that? What does that mean?
Well, we define it to be the point where the moment about that particular point does not depend on alpha. Okay, does that help?
Yeah.
And the aerodynamicist has to determine that by taking the pressure distribution that they compute or measure, as the case may be, and then computing the lift and the moment about some arbitrary position and seeing where along the airfoil that the moment about that particular point doesn't depend on alpha. And there is such a point.
Okay.
Okay. That,
Yeah.
yeah. We don't need to really deal with divergence. We wouldn't really need to introduce the concept of aerodynamic center, except almost all the literature on how the aerodynamic forces are represented is constructed about the concept of using the aerodynamic center, but it's a matter of convenience, really. It's not fundamental in the sense you really need to have that concept to do what we've done.
Oh,
All right. Okay. Let's now take this equation and we can rewrite it a bit. For example, now that we have this definition of divergence dynamic pressure, if you divide through top and bottom by K alpha, this will become 1, and this will become minus Q over Q divergence, right? Do you see that? And by the same token, up here, I'll have a Q over Q divergence times alpha naught. And then I'll have something else here, right? So let's take equation 5. And divide top and bottom by K alpha. I had to divide both the numerator and the denominator, right? Then I can write this as Q over Q divergence times alpha naught plus just to make it a neat formula, and since I said that CMAC is 0 for this special case, also I'm going to set CMAC to 0. Don't have to, but it makes the formula neater. So I have that over 1 minus Q, over Q divergence. Right? Equals alpha E. But now I can divide both sides by alpha naught and write this in a fully compact form. Namely, I have Q over Q divergence over 1 minus Q over Q divergence. And this really gives me the essence of what's going on. Sorry about that. This gives me really the essence of what's going on, because I'm normalizing the twist by the initial angle of attack and seeing how big it is relative to that. And I'm normalizing Q by the divergence Q. I'm seeing how big it is relative to that. if Q over Q divergence is small compared to 1, I just have that, right? But then, now, another thing you can do, so I'll call this equation 6. Another thing you do is you can look at the lift, how much lift I have on my airfoil now that I've allowed it to have an elastic twist. The lift has actually gone up. In fact, the lift also goes in infinity at Q divergence. Well, you want more lift, but you probably don't want that much, right? But it is true that in modern aircraft, we take advantage of the fact that the lift for the deformed wings is more than for the undeformed wing. And you can do that provided you don't get too close to divergence. Because you get too close to divergence, the twist would be too big, you might see the yield stress of material and other bad things might happen. So enhancing the lift by allowing some twist to occur, by getting relatively close, but not too close to Q divergence is not necessarily a bad thing. Okay. Now, there's another thing you can do, and I was talking to a student about this the other day. Another way to look at it is you could take this equation and you could either computationally, let's say, let's talk about the experiment first. If I were in the wind tunnel and I was not yet at the divergence Q, I'm below the divergence Q, I could measure alpha E, and then I could solve for Q divergence at that particular Q. You with me on that? No. So let's do that. Let's rearrange the equation 6 again. We have Q over Q divergence equals alpha E over alpha naught times 1 minus Q over Q divergence. Okay. And now I want to solve for Q over Q divergence. So Q over Q divergence. Oops, sorry about that. Is 1 plus alpha E over alpha naught equals alpha E over alpha naught. You see what I did there? That's okay? Yeah. And now if I want to solve for Q over Q divergence, I have Q over Q divergence is equal to alpha E over alpha naught over 1 plus alpha E over alpha naught. Or if I really want to solve for Q divergence, I'll invert this, and I'll have Q divergence over Q is equal to 1 plus alpha E over alpha naught over alpha E over alpha naught. I'll call that equation 7. Okay. Again, why would I want this? Well, let's say again, I'm below the divergence condition. I'm in the wind tunnel. I measure the twist. Oops, sorry. I measure the twist of the wing. So I know alpha E, I know alpha naught. That's what I said originally. And I know at what Q I'm measuring the twist, right? And then I can solve for Q divergence. So by making a measurement below divergence, I can, if I believe this formula, I can estimate Q divergence. Well, that's a good thing, because if I get too close to Q divergence, I may break my model. Or if I'm talking about a real airplane, the pilot might not be happy to fly too close to Q divergence, but might be perfectly happy to fly below that and with some appropriate sensors measure the twist and from that estimate. Now, in the divergence case, and this would be a neat thing to do in a wind tunnel, by the way, which we've never done, but we could. In the divergence case, most people would say our math models are so good, we don't need to do a lot of wind tunnel testing on divergence per se. But in Flutter, which is sort of the dynamic counterpart of divergence, it's still a matter of intense interest and technical challenge to use a concept like this to measure some dynamic response below the flutter condition to anticipate where flutter will really occur if we ever got there. And typically in models that cost a few millions of dollars and where test time costs a few $100,000 per day in one of the NASA tunnels, where flutter testing is done, you don't want to risk breaking the model. That's not a good day. The model breaks up, you might damage the tunnel, you lose the model, you delay the whole program. So rarely do they test into flutter in the NASA tunnels or the Air Force. We test for flutter all the time here because we have a low speed tunnel. We think we know how to estimate the stress levels well enough, including on the areas that we're not going to break the model. But you wouldn't want to do that necessarily in the NASA tunnel. We've had discussions with the NASA people over the years about doing that, telling them, you really should design a non-linearity in your model so you can test right up to the flutter point and beyond, or in this case, the divergence point and beyond. But so far, they haven't been eager to do that. Okay. I think that's all I want to tell you about divergence. I had some pre-class notes. I want to make sure I hit on all the points I didn't think I did. I don't-
Professor, will the divergence
Yeah.
of dynamic pressure always be less than a flutter dynamic pressure?
No,
No.
no. It can go either way.
Oh, interesting.
To the extent that one is more common than the other, I would say flutter is more common to occur below divergence. In part is because we're much better at predicting divergence with our math models than flutter.
So this would be a non-conservative calculation then in design.
Yeah. No, you always do, you always check divergence. I mean, you always check it. And usually divergence is not critical. Oh, there is an exception, though. I'm glad you asked that question. Yeah, I should draw it on here so Morella can see it too. There was a lot of interest, even dating back to World War II, and more recently on an airplane called the X-29, which was an experimental aircraft that NASA built. And here's a top view. It's a swept forward wing aircraft. Oh, you know the aircraft?
Oh, yeah.
Okay. So here's my fuselage. I'm going to draw it as a stick figure because my drawing skills are modest. So here's the fuselage. And here's the wing. And the flow is this way. So that's swept forward rather than swept back. It turns out if you sweep the wing forward, then divergence is usually more critical than flutter. If you sweep it back, flutter is usually more critical than divergence. And since most airplanes are built to be swept back when they're swept forward, so that's part of the answer to your question.
So
For years, people, well, the Germans in World War II had an airplane that was slightly swept forward, a bomber actually, but it was like 10 or 15 degrees. It wasn't very much. And then after World War II, the Germans built a business jet that was swept forward. And then there was a colonel, what was his first name? Norris was his last name. Colonel Norris in the Air Force, he championed this idea. And this was when composite materials were first coming into the vogue. And it turned out if you build a plane out of metal, it was really hard to build a plane with a swept forward wing that was not so critical for divergence that it made any sense. By the way, the sweeping forward actually has better aerodynamic performance than sweeping back. Okay, so the reason we don't sweep forward is because of aeroelastics. But they did build the X-29. They used composite materials. They tailored it so that the stiffness was of a certain distribution, and they flew it. But no one said, let's go out and build 1,000 of these, right? They decided not to do that.
So does that correlate with the wind tunnel experiment you showed us yesterday, where if you mount the wing here and the free flow is here, the flutter speed is, A, but then when you rotate it to be a control surface, the flutter speed is reduced. So is that an
Oh,
exaggeration?
you're talking about the video
Yeah.
we saw the other day?
Is it-
Yeah, that's interesting. I'm glad you asked that question too. That's a good question. Let's talk about that a little bit. So now we're looking at we're looking at our, it's a cantilever, right? It's a
Yeah,
half
yeah,
wing, right? So, again, I'll draw a stick figure. So here's the wall of our wind tunnel. And now here's our.
Could you move the paper?
Oops,
Thank you.
yeah, sorry about that. Here's the wind tunnel wall. And in this case, it's neither swept forward nor backwards, right? If you rotate it backwards, I think well, if you rotate it backwards, it continues to flutter. That's what we saw in the video, right? If you rotate it forward, which we actually haven't done in our wind tunnel, because we have confidence in computational law, we know what happens. If you sweep it forward, it diverges. As soon as you sweep it forward, the least bit, divergence is more critical than flutter. And so some people have actually swept it all the way forward like this. They call that the inverted flag. If it comes all the way back, right, plant the leading edge, free at the trailing edge, that's called a flag. It's not really a flag, but that's the terminology. And then they have the inverted flag. The inverted flag, you diverge, okay? And there's a group at Caltech, Garib, Professor Garib and his students. He's had several PhD students who looked at the swept forward case, the flag. And what happens is it diverges. But then if you go past the divergence speed enough, there's nonlinear. There's a nonlinearity in the structure that prevents it from going off to infinity, right? But then if you go past the divergence speed by a sufficient amount, then the deflection gets large and you get a vortex off the leading, what is now the leading edge of this inverted flag. And that causes the flow itself to oscillate, which in turn drives the flag. And they say, well, gee, that's great. We have this large motion. We put some piezoelectrics on it. Maybe we can generate some electrical energy, right? So that work has been going on for some time. When we did our test, we weren't particularly interested in the swept forward case or the inverted flag. We were more interested in the other case. Yes.
What does divergence look like?
What does it look like? Okay, meaning physically? Okay, so let's say, well, gee, Morella's not gonna be able to see this. Well, yeah, let me now look. This is a top view, right?
Could you move the page up?
And now let's look at a
Dr. Dowell,
in view.
Dr. Dowell.
Hmm?
Good move.
Oh, sorry about that. There's the top view. Now let's look at an in view. So here I'm going to be looking edge on, right? Okay. So yeah. So now yeah. So now I'm cantilevered at the trailing edge. The flow is this way. And let's assume I can line this perfectly with the flow. So nothing much happens. It just sits there until I get to the divergence speed. That's not quite true because you can't align it perfectly. So there's a little bending, the non-alignment, right? It could bend up, it could bend down, but it's very small. And then when you get to divergence, you begin to get a bending like this. Okay, this is when I'm beyond the divergence flow velocity, which also corresponds to a certain value of dynamic pressure. And then as I go to larger and larger values, and I just keeps bending more and more until I break it.
So is this,
So it looks like a parabola, basically.
this incorporated in the alpha E term?
Yeah,
This
this would
information?
be alpha E, but
Okay.
remember our linear model will not predict what happens after divergence. Okay, it only predicts where the divergence, the flow velocity at which the divergence begins. If I want to predict the rest of this, I had to put in a nonlinearity in my model. And it turns out for small excursions beyond divergence flow velocity, is principally the structural nonlinearity. So when if I have a cantilevered beam like this, there's actually a nonlinear stiffness when I get to larger and larger deflections, and that governs the shape. The shape can be predicted by linear model, but the actual absolute amplitude, I would have to use a nonlinear model. That, yep, yep. Okay, now let me go back and see if I hit all the points I wanted to hit. I think I did. Oh, yeah, we got time to do that.
Dr. Dowell, I have a quick question.
Okay, go ahead.
What are some advantages of a forward swept wing?
It's principally the aerodynamics. It has to do with, if I recall correctly, and it's been a while since I've thought about it. There's flow separation. This was going to be a fighter aircraft. It's a fighter-like aircraft, so it's going to go through fairly severe maneuvers. And there was concern about flow separation, and the flow separation pattern is more favorable on the forward swept wing than the backward swept wing.
Okay.
And I'm trying to remember which way it goes now. In the three-dimensional wing, the separations, if you're swept back, I won't remember. And one of them, the separation begins at the tip and moves toward the root. The other one starts at the root and moves toward the tip.
Okay.
I'm having trouble remembering which one is which and which one is more favorable.
To the fuselage.
Yep.
Goes towards the.
So let me talk with words, and maybe that'll help a little bit. If we want to do a dynamic analysis, we have to account for the inertia in the system, right? And since this is just torsional motion, we need a moment of inertia, a mass moment of inertia, times an angular acceleration. So we need a term like moment of inertia times alpha, second time derivative of alpha, right? Then we don't want to have a linear algebra equation, linear algebraic equation. We have a linear ordinary difference equation in time, right? To determine alpha sub E. But we can do that. And when you do that, you discover what happens is that below the divergence condition, if you excite the system and look at its time history, it just oscillates at some frequency. Right? We have no damping in the model initially. We could put damping in too, but just putting in the inertia term, it'll oscillate with some frequency. That frequency will change as you change the dynamic pressure. In fact, frequency goes to zero when you reach the divergence dynamic pressure, which is exactly what happens when you have a beam with inloads and it buckles, right? If you look at a beam and you put a compressive load on it, its frequency, its resonant frequency goes down as you increase the inload till you get to a point where the frequency goes to zero, and that's the buckling point of the beam. Same thing happens with divergence. And then the dynamic analysis also tells you that beyond divergence, the system is dynamically unstable, and given any initial condition, the oscillations have zero frequency. So it's just an exponential growth in time beyond the divergence condition, which is exactly what happens in buckling of a beam under frequency inload as well. But if you looked at our formula, which we can't see it, but our graph is not working. Our formula, if you look at the formula for what's happening once we're beyond the dynamic, remember, the divergence dynamic pressure, what's happening is that the deflection is getting larger and larger below the dynamic pressure for the divergence. We're going to infinity, but then once we go beyond that, our formula says we come back from infinity, right? We get a finite answer, but that answer is not meaningful physically. because we've gone beyond the limits of our mathematical model. And the dynamic analysis tells you that more explicitly because it shows that you get exponential growth in time once you go past the divergence condition. And you don't see that from static analysis. So the static analysis is fine for finding when divergence starts. And that for the linear model that we've been discussing today, that's all you can get out of the linear model. To find out what happens beyond divergence, dynamically, you need a dynamic model. And for the linear dynamic model, it will show exponential growth in time. But then if I had a nonlinearity, it would show an exponential growth in time, but then it would saturate as time goes on due to the nonlinearity. And you can find that from a dynamic analysis. So what I was going to do, I was going to assign that for a homework problem.
Good.
But I think what I'll do, since we can't do it with the camera, I'll write that up and send it to you via an email. But that, did I tell you enough that at least you think you know what I'm hoping you'll do? Yeah. Okay. You can do it. It's going to be a second order difference equation in time. Linear, right? You probably solve such an equation at some point in your previous career. Any further question? Is Morales still with us?
She had to leave.
Oh,
she
did she?
said.
Okay. Any further questions? Yes.
So are we omitting viscosity because it's not a huge factor?
Uh-huh.
Like usually in the lift term, there's the pressure part and then there's the viscosity part. So is the viscosity part just so small that it doesn't affect this equation much?
Now tell me that one more time.
Like a typical lift term is comprised of the pressure component and the viscosity component, correct?
Yeah.
But we're omitting the viscosity component just because it's so insignificant.
We're talking about the CMAC term?
Just in general, like in this entire derivation, there was no viscosity. So if we were to add viscosity, would it change this
If we were to add which term?
viscosity?
Oh, viscosity. Well, these formulas I've given you all assume there is no viscosity. So they're approximations.
Right.
Yeah. If you added viscosity for the divergence condition, typically it would not make much difference.
Okay.
Almost all initial divergence and flutter analyses are done using inviscid theory, and not just inviscid theory, but using potential flow inviscid theory. So there's a hierarchy of flow, and you may encounter this in your previous work. You start usually with potential flow theory, and then and that's fine up to the point where you get some shock waves. And then when you have a shock, you may need to go to the so-called Euler equations. And then if the boundary layer were thick enough, or there were interaction between shocks and the boundary layer, then you might need to add viscosity. That's most likely to be of significance again in the transonic range, or perhaps in the supersonic, hypersonic range. In the low speed range, for example, in the work we do in our tunnel, viscosity usually is not an issue unless you go to very high angles of attack. In that video, we talked about going to 40 degrees or something like that. And so when you get to 40 degrees and you have those severe oscillations of the fluid alone, that definitely is the case where viscosity is needed. You know? But for small angles, streamlined flows, low speeds, viscosity is usually not an issue. One exception to that might be the control surface. If you have a control surface, there's usually a gap, an air gap between the control surface and the main wing, and then viscosity might play a role there. But even if you run an average Stokes code, they usually don't give you a very good model of that. And so people tend to use empirical factors and take the classical potential theory and multiplied by a coefficient. They said, well, that control surface is only half as effective as we think potential flow, as we would think of potential flow theory. So they'll multiply all their numbers by 0.5. It's really that important.
Okay,
Yeah.
thank you.
Yeah. Good question. Okay, I'll write up the homework and you're reading up to up to page 25, right? So we'll go ahead next time and talk about control surface reversal and make the homework due a week from next Tuesday. That's fair, isn't it?
Yeah.
Yeah.
Yep.
Yeah, okay. Other questions before we conclude the day? Yes,
So is divergence independent of drag as well?
usually.
Okay.
Usually, yeah, drag forces are usually not important in aeroelasticity, except that if you have an engine on a wing, that engine has enough frontal area and it lies far enough away from the wing itself, then that drag times that moment arm might tend to twist the wing. And people have included that for very flexible wings with very heavy engines. People have looked at that. It's usually not a major factor, but for a specific design, it might be. And it is true that the commercial airplanes are beginning to have longer and longer spans, and the engines are getting bigger and bigger. So and that may become more important in the future than it has been in the past. But people have looked at that. But what they usually do is they just include what I'll call the static thrust of the engine times that moment arm, what tends to twist the wing. And then it's what is called a follower force, in the sense that the force itself and the moment magnitude isn't changing, but the direction is changing because the wing is twisting. So that can give rise to a change in divergence or flutter. But normally, I would say when you're first designing a wing for aeroelastic, you probably don't include that fact unless you have some reason based on prior experience for things that's going to be important. Next question. Other question. Okay. We'll gather again on Tuesday.